This cake is yummy. Can you please share the recipe with me? I love baking.
Sure. For baking this cake, I use 2 eggs, a cup of flour, a cup of sugar, and a cup of butter.
If I have 6 eggs, can I bake a bigger cake?
6 eggs are too many. For this cake, follow the proportion. If you want a bigger cake, increase the ingredients in the same proportion.
In nature too, you will find substances combined in fixed proportions. For instance, the law of constant proportions and the law of multiple proportions explain how various elements combine to form different compounds. This lesson is about laws of chemical combination and an introduction to an atom. At the end of this lesson, you will be able to explain the law of conservation of mass, describe an experiment to prove the law of conservation of mass, explain the law of constant proportions, explain the law of multiple proportion, list the postulates of Dalton's atom, define an atom, identify the symbols of elements, identify the atomic mass of elements, define a molecule, identify the atomicity of elements, define an ion, define valency, list the rules for writing a formula, and apply a set of rules to write a formula. After a series of experiments, Democritus concluded that if you continue to cut a stone into smaller and smaller pieces, at some point you would reach a piece so tiny that it could no longer be divided. Democritus called these infinitely small pieces of matter atomos, meaning indivisible. Convinced that matter is made of tiny, indivisible particles. Many scientists like Evangelista Torricelli, Daniele Bernoulli, Joseph Priestley, and Antoine Lavoisier started studying the natural world. Among them, Joseph Priestley discovered that substances could combine together or break apart to form new substances. Later, Antoine Lavoisier, from his experimental observations, established a law that states that there is no gain or loss of mass when new substances are formed. This can be better explained with the help of an experiment. To do this experiment, take 5 grams of iron filings in a watch glass. Take 5 grams of sulfur in another watch glass. Then, mix the iron filings and the sulfur thoroughly and weigh it. The weight is 10 grams. Now, heat the mixture. It forms a dark molten mass of ferrous sulfide. Weigh it. You'll find the weight to be 10 grams. This shows that the mass is the same, though there is a change in form. Therefore, the law of conservation of mass can be stated as: in any chemical reaction, the total mass of the substance before and after the reaction is the same, although its matter undergoes a physical change. The total mass of reactants is equal to the total mass of products. This led scientists to ponder over the combination of substances, and they conducted various experiments. All these observations were accepted, and the law of definite proportion was proposed by Proust. Proust, a French chemist, concluded that when 100 grams of water was decomposed, 11 grams of hydrogen and 89 grams of oxygen was obtained. He later purified and analyzed numerous compounds and concluded that every pure substance contains the same elements combined in the same proportions by weight. So, the law of definite proportions can be defined as: in a chemical substance, the elements are always present in definite proportions by mass. Hydrogen and oxygen can combine in different proportions to form different compounds like water and hydrogen peroxide. 2 parts of hydrogen combine with 1 part of oxygen to form water, and 2 parts of hydrogen combines with 2 parts of oxygen to form hydrogen peroxide. This follows the law of multiple proportions. According to this law, when 2 elements combine to form 2 or more different compounds, then the weight of one of the elements is constant and the other has a simple ratio. Basing on Proust's observations, John Dalton further researched and realized that water could exist as a gas that is mixed with air and occupies the same space as air. Solids cannot occupy the same space as gas. For example, ice cannot mix with air. This made Dalton ponder over what could allow water to sometimes behave as a solid and as a gas at other times. After a series of experiments with various substances in different states, Dalton concluded that all matter must be composed of tiny particles which cannot be further divided. He called them atoms. So an atom can be defined as the smallest particle of an element. According to Dalton, all matter is made of atoms. Atoms are indivisible and indestructible. All atoms of a given element are identical in mass and in properties. Compounds are formed by a combination of 2 or more different kinds of atoms. And a chemical reaction is a rearrangement of atoms. Having identified some elements, Dalton proposed a scheme of notation to represent elements. For example, hydrogen was represented as, carbon as, oxygen as, nitrogen as, sulfur as, phosphorus as, copper as, silver as, gold as, iron as, chlorine as, tin as, zinc as, and lead as. The symbols used today were suggested by Berzelius. The first letter of the symbol is always in uppercase. Some elements were represented by the starting alphabet of its name. For instance, carbon is represented as C, boron as B, oxygen as O, sulfur as S, nitrogen is written as N, and hydrogen as H. All the elements do not follow the same convention. Symbols of some elements were the first 2 alphabets, but the second alphabet is in the lower case. For example, aluminium is represented as Al, chlorine as Cl, argon is written as Ar, beryllium as Be, and lithium as Li. An element is represented by either the first or the first and any other letter of its Latin name. There are some exceptions while writing the symbols for some of the elements. These names were derived from Latin. In general, the first letter and the second letter of their Latin names are used to represent the symbols of these elements. For example, antimony is called stibium in Latin, and the symbol is Sb. Copper is known as cuprum, and the symbol is Cu. gold as orumand, represented by Au. Iron as ferrum, and the symbol is Fe. Lead as plumbum, and is represented by Pb. Mercury as hydragium, and is represented as Hg. Kalium is the Latin name of potassium, and its symbol is K. Silver as argentum, and it is represented as Ag. Natrium is the Latin name of sodium, and is represented as Na. The Latin name of tin is stannum, and the symbol is Sn. Wolfram is the Latin name of tungsten, and it is represented as W. A symbol not only represents one atom, but also the mass of the element. According to Dalton, each element has a characteristic atomic mass. Scientists initially took the mass of oxygen as standard mass, since oxygen formed a large number of compounds. In 1961, carbon-12 isotope was chosen as the standard reference for measuring atomic masses. The relative atomic masses of all elements have been found with respect to an atom of carbon-12. For example, in a bakery, if a cake is cut into 12 equal pieces, he is able to find the mass of each confectionery item relative to the mass of a single piece of cake. Now, he sells the confectionery by relative confectionery mass unit. Similarly, the relative atomic mass of the atom of an element is defined as the average mass of the atom as compared to 1/12 the mass of one C12 atom. Matter is made of atoms. But how do these atoms exist? These atoms exist in a combined state called molecules. Thus, a molecule is the smallest particle of an element or compound that can exist independently and show all the properties of that substance. Some elements like sodium, potassium, and helium exist as single atoms, and others like hydrogen, oxygen, etc. exist in a combined state. Atoms combine to form molecules. The molecules of an element are constituted by the same type of atoms. For example, elements like hydrogen, oxygen, phosphorus have more than one atom in a molecule. This number is specific for an element and is known as its atomicity. Thus, the number of atoms constituting a molecule is referred to as atomicity. Let us look at some examples. An oxygen molecule has 2 atoms of oxygen and is known as a diatomic molecule. Hydrogen, chlorine, nitrogen, etc. also exist as diatomic molecules. Elements like phosphorus and sulfur have more than 2 atoms in a molecule and are called polyatomic. A phosphorus molecule has 4 atoms of phosphorus, P4, and a sulfur molecule has 8 atoms and is octaatomic, S8. So far we have discussed about the molecules of elements. Elements combine to form compounds. Thus, a molecule of a compound has 2 or more elements. For example, common salt is a compound of sodium and chlorine, where sodium is a positively charged particle, and chlorine a negatively charged particle, and each of this is called an ion. Thus, a charged particle is called an ion. The positively charged particle is called cation. On the other hand, the negatively charged particle is referred to as anion. We know that atoms of an element combine to form a compound. Every atom has a specific combining capacity. This combining capacity of an element is known as valency. For example, consider a water molecule. It has 2 atoms of hydrogen and 1 atom of oxygen. This shows that the combining capacity of oxygen is 2 and takes 2 hydrogen atoms. Similarly, sodium monoxide has 2 atoms of sodium and 1 atom of oxygen. Thus, the combining capacity of sodium is 1 and oxygen is 2. Here the compound is formed by 2 different elements, and such compounds are called binary compounds. Some compounds have more than 2 elements or a group of elements as ions. For example, an OH ion. It consists of hydrogen and oxygen atom, and its valency is 1. Here are the valencies of some elements. Chlorine has the valency of 1. The valency of magnesium and calcium is 2, while nitrogen and aluminium is 3, and that of carbon is 4. A nitrate ion and an ammonium ion show a valency of 1, whereas carbonate and sulfate have a valency of 2. The knowledge of valency helps to write the formulae of compounds. A formula is the shorthand representation of a compound. For example, consider a water molecule. It has hydrogen and oxygen. The symbol of hydrogen is H and oxygen is O, and its formula is H2O. Let's learn to write a formula. To write the formula of compounds, we follow a set of rules. Let us write the formula of calcium carbonate. First and foremost, identify the elements present in calcium carbonate. They are calcium, carbon, and oxygen. Identify the cation and the anion. In calcium carbonate, calcium is the cation and carbonate is the anion. Next, identify the valency of the cation and the anion and place it just above the symbol. For example, the valency of calcium is 2 and the valency of carbonate is also 2. Then cross-multiply the valencies. Now write the numerals as subscript right after the respective symbol, Ca2 and CO32. In case of calcium carbonate, both the valencies are 2, hence the formula is CaCO3. For compounds formed with polyatomic ions, the ion is enclosed in a bracket before writing the number of units. For example, ammonium sulfate. It has both ammonium and sulfate ions. The valency of an ammonium ion is 1 and sulfate is 2. When we cross-multiply, ammonium has a subscript 2. This 2 is written outside the bracket. There is an exception for some of the metals, which exhibit variable valency and are named accordingly. For example, copper shows 2 different valencies, 1 and 2. In such a case, the compound formed with lower valency is called cuprous, and the compound is cuprous oxide, that is, Cu2O. On the other hand, copper with valency 2 forms cupric oxide, CuO. Similarly, iron also exhibits variable valency. Iron with a valency of 2 is ferrous, and iron with a valency of 3 is ferric.
Hey, what is this? I wonder what these people are doing. Do we weigh coins? Till now, I thought that coins are only counted.
Yes, they do.
But why?
Because it is very tedious to count coins. They weigh them instead. Bankers know that a fixed number of a particular type of coin always has the same weight.
Amazing! This reduces a lot of time.
So, the bankers link the mass of coins to the number of coins present. Here's another example. In a laboratory, when experiments are conducted using elements or compounds, the mass of an element or compound is taken into consideration, rather than counting the number of atoms that an element or compound contains. This lesson is about the concept of a mole. At the end of this lesson, you will be able to explain the concept of a mole, calculate molecular mass, a formula unit mass of a given molecule, apply the concept of mole and molecular mass to solve given problems.
So, how can they arrive at a conclusion that mass equals the number of atoms?
Atoms and molecules, being very minute, have tiny masses. It is practically not possible to find the mass of one atom or molecule or ions. Hence, a bigger unit called mole is introduced. Then, 1 mole is defined as the amount of substance of a system which contains as many entities like atoms, molecules and ions as there are atoms in 12 grams of carbon-12. Scientists, through various experiments, found that the number of atoms present in 12 grams of carbon-12, which is equal to 6.022 multiplied by 10 to the power of 23. This means the atomic mass in grams of an element contains 6.022 multiplied by 10 to the power of 23 atoms of that element. This number was called mole by scientists. A mole is a constant, definite number of atoms of a particular element. For example, when your mother asks you to get a dozen apples, how many would you get?
It means 12, obviously.
Similarly, a mole is also a constant and a definite number like a dozen.
A mole.
Scientists, after a series of experiments, concluded that 1 mole of any substance contains 6.022 multiplied by 10 to the power of 23 number of atoms. Here is an example. The number of atoms present in 12 grams of a carbon-12 isotope, which is equal to 1 mole of carbon, contains 6.022 multiplied by 10 to the power of 23 number of atoms. Similarly, 16 grams of oxygen and 14 grams of nitrogen, which is also equal to 1 mole, contains 6.022 multiplied by 10 to the power of 23 number of atoms.
So, it is a constant.
Yes, you are right. This number is used as a constant and is called Avogadro's number.
Avogadro's number?
This was named after the Italian chemist Amedeo Avogadro.